Well, thank you. I'm aware that there's little time, so I just very briefly introduce myself. My name is Volker Sorge. I'm a now 20% professor at University of Birmingham, and I spend a lot of my time these days working for other organizations. And one of my hats is, in particular, I'm a member of the MathJax Consortium. And if you're not familiar with MathJax does all the rendering of LaTeX out there on the web. And in the background, there is a kind of an accessibility engine, which makes it accessible if you know what you're doing. And that engine is primarily my work, which I've been maintaining for the last 10 years, since I've implemented it during a year while I was at Google in Mountain View. And somebody mentioned Equatia earlier, and in there, for instance, that's my engine that's doing the text-to-speech for mathematics. So if you have any complaints about it, by all means, file issues on our GitHub repositories. And then once you're filing issues, think about it, motivating your universities to also sponsor our project. That's always helpful. Anyway, but this is not actually what I'm here for to talk about. I'm actually want to talk about how to create accessible STEM diagrams. And this is something which I'm doing a lot with my other affiliation, particularly with my own company, which is called Progressive Accessibility Solutions. So I'll give you a bit of background. Obviously, in a group like this, I do not have to motivate why graphics and figures are important in STEM education. But I probably should motivate why they are so badly supported in the web environment at the moment. So some of you might be familiar with the WCAG criteria. So that stands for Web Content Accessibility Guidelines. And they specify that for images, an alt text is sufficient, right? They don't even say that you have to have a longer text by an area described by or anything of that nature. I've been a member or an invited expert of a number of these W3C groups, and whenever you come across these topics and say, you know, we need more support, particularly for images in STEM and diagrams, then normally there's a big pushback from major companies. I'm not going to name the companies, but you probably all know the companies I'm talking about. And the problem is with these, just providing an alt text is generally not enough for a STEM diagram. Because imagine you want to convey the meaning of a STEM diagram just in text within a tweet. Very difficult, very difficult. And moreover, even if you have a good description, they can be very, very long. So from my point of view, at least, interacting with the diagram is very important, that you can actually understand what the single components are. And then finally, so a lot of people think, unfortunately, that, you know, it'll all go better. We get all this great AI now. Well, if you play around with some of these AIs, I've linked to the caption bot here, which is from Microsoft, for instance. It doesn't give you normally a very good, let me just use it on this photo and picture, doesn't normally give you a very good description. And now the description for this images, if you can't see it, I'll read it out for you. I seem to be under the weather right now. Try again later. Well, that's not very helpful. Thank you, Microsoft. Anyway, so what I would claim for STEM, you always need precision. Precision is important. It really is not good enough just to say, well, this is a graph, this is a chart. You really need to explain what's in there. And I think the first speaker in this session made it very clear how detailed these explanations have to be. Now, the question is, where do you actually get these explanations from? You know, you can employ somebody who writes them one by one, or the other idea, and that's the idea I've been researching on for the last 10 years primarily, is how to get them into the diagrams automatically, how to source them so we don't have to worry about where they're coming from, but they'll just come into the diagram pretty much automatically. And the way to do this, and the route we're normally taking, is by using SVG in a web environment. SVG stands for Scalable Vector Graphics, which means that you have a nice graphic which scales when you zoom, no matter what the size. You can easily change colors in it, and you can you can have structured content in there. You can group things together that make sense in a semantic way, and then you can add explanations and content to it without altering the visuals. That is, you can embed information, speech, as well as navigation information and other information, so that you, for instance, can 3D print it, you can immediately emboss it on your embosser, you can just have it read by a screen reader and so on. And it's still the same diagram. But those people who do not need assistive technology, all they see is the diagram. And that's normally good enough for the authors. So the main idea is, okay, we want to create an SVG which represents a STEM diagram. Where are we going to get the semantics from? Where are we going to get these explanations from? And one major problem there is that STEM subjects, in many ways, they are living languages. Right? So the whole point about a STEM subject is that it creates new concepts on a daily basis. Research is moving forward. So we need more and more, and every day we need more vernacular and different vernacular. And as such, it's not really possible at some point to say, okay, well, let's just put a declarative standard out there which describes all the concepts in physics, describes everything we ever have in math. It doesn't really work. And we've seen that there's been plenty of failed attempts. MathML is a classic example of a failed attempt, particular content MathML of a semantic standard. There's others out there. So in other words, we need something where we can kind of do things automatically, and maybe with a database in the background that can be updated much more easily than any standard could ever be. And another question then, well, what about authors? Now we want authors to put the knowledge in there. Well, if we know authors, and many of us are authors, and I'm particularly an author or a teacher or a lecturer, that component normally fails because everything has to be put together quickly, normally just briefly before the deadline, 3 hours before you actually give your lectures, you put together the lecture material, you then put into some horribly inaccessible format like PDF, and then you give it to your students. It's not really not really practical. So therefore, the techniques we're exploring are primarily automatic and should work as automatic as possible. The idea is that you take the source, whatever the source is, you try to understand what it means, and then use that meaning in order to generate an explanation, embed it into your SVG, put it on the web, make it accessible for everybody. And for the rest of the talk, I'll primarily show you examples now. And the first example has nothing to do with mathematics. It's chemistry. Why is it chemistry? Because that's where our technique has worked the most successful, and we actually got a product to market with this. And the nice thing about chemistry is very well defined. Molecules are very well defined, and the way we go about making chemistry accessible is by taking, for instance, an image, a bitmap image, a PNG, a JPEG, a GIF, or whatever you have, and then try to understand it, do document analysis or image analysis and image recognition on it in order to understand the chemistry in there, and then use that understanding in order to make it accessible. Here I have an example of a large molecule. This is from a US patent application from 2002. And I can make it a bit larger for you. For those who can see it, this is a totally inaccessible bitmap. This is a PNG. You can see the larger I make it, the more you can see jagged bonds or lines and so on. So it's not an SVG. So what we do is we recognize it and we then put it into an SVG, and that SVG is accessible. And here's the SVG that comes out of it. And if I make it larger, it works very well. It zooms nicely, it rescales. And what I can do now is I can actually make this accessible, or it is already accessible here on the page. So the page here is an HTML page. So all my slides are accessible as well. It's an HTML page. All I do is now and it starts talking to me. Can you hear it talking? Can anybody give me feedback whether you could hear?
I can't hear, Volker. I don't know if
okay,
can, but
I might have forgot to share the screen with sound. Let me just do that very quickly. Okay. Of course, now I'm sharing the wrong screen, typical. Share the screen. That's the right screen. Let's do that again.
Fused ring system phthalate with 2 subrings substitution at position 2.
Did that work for anyone?
Yes. Mhm.
Well done. Okay, sorry for not sharing the sound immediately. I should always remember that. So what happens there is information about the molecule has been computed and has been put into the diagram. And moreover, it has been put into in a hierarchical way, so you can kind of
Ceramicine.
read it at the top level, and then you can start diving
Fused ring
into
system
there.
phthalate with 2 subrings substitution at position 2.
And then you can walk inside the molecule, experience stepwise in a chemical correct order.
Piperidine ring substitutions at positions 1 and 4.
And it's an SVG, so you can do all kinds of trickery with it. So for instance, you can change the background colors, foreground colors, all these things, put it into a dark mode and all of that. What you can also do is you can, in the same, and I'll show that for you on a different page, you can also embed multiple languages.
Aspirin.
Here's an aspirin. Let's listen to aspirin in.
アセチルサリチル酸
Now that's in Japanese.
Acetylsalicylsäure.
That's the same thing in German. You can still walk it.
Benzenring mit Substitution an Position 1 und 2.
Benzene ring substitutions at positions 1 and 2.
And this is kind of the idea of how to make diagrams accessible on a website. And obviously, this happens now from actual source material, which are bitmap graphics. However, once you have more information about what you want to make accessible, then it's even easier. So for instance, for chemistry, you can use chemical identifiers. For other things,
N-butane substitutions at positions 1 and
let me stop that talking. Let's go to the next slide instead. If you have more knowledge about what you're doing, in particular, if you have the data that originally generated your diagram, then of course you can do a lot more than just, trying to understand what somebody has drawn. So some of the work that I've been doing, in particular, I've been doing with a statistician in New Zealand, Jonathan Godfrey. So some of you might have come across Jonathan's work. Jonathan Godfrey is a blind statistician. He's working at, I think it's Massey University in New Zealand. He's put out a package called Braille R, which is effectively a package that tries to make R accessible, and in particular, the graphics that's being generated in R, the data visualizations. And he originally envisioned them to just be embossable with Braille labels. What we've done now is we effectively take these data visualizations and we make them accessible in a very similar fashion to what we're doing with the chemistry. And I'll show you an example here. Oops, which one am I going to show you? Say this first one here, for instance, is an example that's histogram of ozone.
histogram of ozone.
I can go in
Title, histogram of ozone. X-axis, ozone. Y-axis, frequency. Histogram bars. Bar 1 at 10 with value 37. Bar 2 at 30 with value 34.
So if you can't see it, what I'm doing right now, I'm stepping through the histogram, and it kind of tells me all the bars and so on.
Bar 3 at 50 with value 14.
Right. And this is...
Sorry, just to let you know, Volker, just 1 minute.
Oh, I should hurry then. Okay, right. Again, all this doesn't just work on particular web pages, it works on any web page. Here's, for instance, the same in my slides. And finally, what I would like to show you is what we're currently doing. So I'm doing that with David Austin from Grand Valley State. We're using pretext, and where pretext is effectively an XML language which embeds LaTeX. And we're using that in order to make graphics accessible from Tixi straight out of the box with a minimal graphics language. And let me show you our paper that we've just submitted somewhere, and it's fully accessible. Just effectively think about it, a LaTeX document that has been transformed into a fully accessible HTML document. And I'll show you very briefly that it's accessible On the math level, for instance, here's an expression, not very much in there, math in there, but here's one, which is, if you can't see that, I should have to switch on a screen reader, but it's math checks, it's raised f of 1, and you can explore it and so on. But what's more exciting is, for us here, is that all the graphics that are in there, they're accessible. For instance, here's one, here's the example graphics, which we can make accessible straight out of the box. I'll start one.
The graph of a function and its first two derivatives. The coordinate grid and axes. The graph of f.
And what you can also do is you can make this sound. Effectively you can include sonifications into your graph, and everything automatically is being made accessible just with this kind of small extension to the pretext language, in which you can then embed, I think, the computer algebra system that does the actual computations is Sage, and all that comes out as SVGs. My apologies, I think I've run out of time, but I have everything on the slides, and if the slides are a single web page, so you can play with them as much as you like after the workshop. Thank you very much.
Okay, thank you very much, Volker. Okay, so I'm just going to move on, but just obviously feel free to interrupt me and jump into the conversation, or raise your hand if anybody's got a question in the chat. I see there's a question from Vincenzo, who's asking for you, Volker, about how you're generating, I think, the voiceover for the chemical structure, and whether that's implemented within the SVG. And I had actually similar question: is that something that's already coded? Because that's obviously, this is a well-known molecule, so is that already there on the web? Or did people come in and had to implement that in the code? Because I guess from the staff perspective, something I hear all the time is we don't have time to invest and do all these descriptions. So if they already exist somehow, that could be helpful.
Right. So all this is, I didn't have time to go into any of the technical details there. So what happens is you take the image, or you take a chemical identifier like an INGI key or a SMILES representation, and from that a molecule is generated. So all the accessibility is automatically generated. The way it works is there's a semantic analysis and pattern matching program behind it, and it kind of takes it apart and it throws certain things out to web services where you can automatically name things. So none of this is in the system. The only names in the system are the atom names, and everything else is automatically generated and put together. And then technically the way it works is you effectively have an SVG. Inside that SVG, you have a little, in a different namespace, you have an XML structure. On that XML structure, you have a bit of JavaScript magic, which walks on that, highlights things, zooms things, whatever, and thereby also triggers the web audio API or web speech API in order to speak it out. Right? If you have a screen reader running, it automatically sends it to the screen reader. So this is there, and you can, so we have effectively, we've got a product online, and you can go and you can just convert your own. We're currently revamping it, but you can just convert your own favorite molecule into an accessible molecule.
Yeah, I guess it works. I've got a kind of more general comments really about this, is that sometimes the reason I use graph and figures in my teaching is because it's so much more efficient than a lot of words. And I kind of find trying to describe my figure in the alt text or in the SVG content is very difficult for me, because the reason I use figure is because I'm not able to use words efficiently to explain what I want to explain. And I think it's where I think there is kind of a link with what Ben was telling us about, and give us some standards and some guidance as to how we should be describing our figures. So yeah, I think I find it although I see the great interest in doing this, I think I, as a practitioner, would find it really difficult to try and quote some description of my figures and diagrams. Ben, I don't know if you want to come in and make some comments around this, or Volker, if you have further comments.
So my comment here would be, okay, for chemistry, it's fairly easy because chemists know how to talk about that things. For math, it's not that straightforward. So what we do in the pretext project, for instance, is first of all, there is a lot of this kind of you can do with standard descriptions, and then you can have the author put in some additional customized descriptions. However, what we generally experience is that it's a lot easier for people who have to describe those diagrams if they at least get an automatically generated template, and then just tap things and say, well, actually, I would like this to be named like this and this piece in a slightly different order, etc. That's I think is much more helpful. And another thing about the pretext project is, of course, you can generate a lot of alternative formats out of it. So it's not just the speech on the website. You can also use this in order to get a tactile output, for instance. So if you really want to dive into your graphics, then get an embossed tactile output for your graphics, and then you can experience it that way as well.